Let's look at the scientific method, right? So we're going to be doing some science here. Right? Science works. So scientific method is a framework for gaining and organizing knowledge. We get a set of facts with a plan of action. It is a procedure for processing and understanding certain types of information. The scientific method is the basis on which a scientific inquiry is conducted, and it varies according to the nature of the problem encountered. So we will see the classic scientific method here. Right? The science is a sequence of science used in the study of nature, and it's going to help solve problems effectively because it gives us a framework to analyze things, hopefully, objectively. Right? Mastery of the scientific approach makes for excellent problem solving. So this is the classical method, right? You've got some observation. You form a hypothesis about that observation. So a hypothesis is just an idea you can test. It's a testable idea. You test that idea by running an experiment, right? And you keep going through this cycle. Right? Then from there, you can build a theory or a model, which you can use to make a prediction. If that prediction holds up, you're going to run another experiment, and then you modify that theory as needed. So the key is that this is an iterative process. It is always changing. It invites what we call scientific skepticism. And one of the interesting things about science is that, one, this is a way oversimplified version of what really happens, but it's also not exactly how the scientific process works when you're actually in a research lab. So this is a very abstract version of that. So let's look at our theory. It's a set of tested hypotheses that gives an overall explanation for some natural phenomena. An observation is a witness phenomenon that can be recorded. Right? So what makes science different from mess around and find out is science is mess around, find out, and write it down. Right? So you can replace mess around. And interpretation is a possible explanation for the result behind the phenomenon. And oftentimes this interpretation is wrong or needs modification or is something that undergoes revision. Science is always changing. A natural law is an observation that applies to many different systems. We're trying to get away from that language of natural law because if you think about something like even Newton's laws of motion, right? So you can't think of anything more dead set than Newton's laws of motion. Every action has an equal and opposite reaction. Body in motion tends to stay in motion. Well, some of those Newtonian mechanics we found out at the beginning of the 20th century start to break down when you get down to the quantum level of things. So we try to avoid using law now. But we do have some things that we will still refer to as laws. For example, the law of conservation of mass, which says the total masses of materials is not affected by a chemical change in those materials. A law is a statement of how a particular phenomenon occurs, and a theory is an attempt to explain why a phenomenon occurs. So the history of chemistry. The Greeks were the first to attempt to provide a reason behind what we see as chemical equations and reactions. They believed, or Empedocles believed, that all matter was composed of earth, air, fire, and water. Empedocles was an interesting fellow who kind of threw himself into a volcano and is kind of one of those, well, I'll show you guys kind of things. Alchemy was the prevalent mode of chemistrying for the next 2,000 years. Several new elements were discovered during that time, so progress was being made. It's just that the intellectual framework was based on primarily this Empedoclean version of what constitutes an element, and they didn't have the scientific method available as a tool or framework to do some of their analyses. And the way in which they conceived of the universe also prevented them from making some of the scientific discoveries that we have now. Many methods were prepared for mineral acids that were developed. In many ways, one of the things I did as my master's degree was look into alchemy and literature, and so I've read quite a bit about alchemy and the development of different assays, for example, using acid to attack fake gold. So real gold will undergo an assay, and it will not dissolve in the presence of certain acids, whereas something like iron pyrite would. Robert Boyle is really the person we consider to often be the first chemist. You've got other guys working at the same time, Gay-Lussac or Black up in Scotland. So, and Boyle was quantifying the relationship between pressure and air. So, kind of looking at that history, we've got alchemy that happened in the Middle Ages. We transitioned to applying material and what we would think of as chemistry to medicine, and that's called iatrochemistry, so medicinal chemistry now. And one of the forefathers of that was this guy, Paracelsus, so also known as Theophrastus Bombastus von Hohenheim, who was kind of one of the big pioneers of applying chemistry to medical problems. And then, after we've developed the scientific method, age of enlightenment, age of reason, we now have the technological society we live in today. Right? So here is a funny slide that has, this is our classical structure of what an element looks like, where we've got earth, air, fire, and water, and the combinations between them, right? You combine water and earth, and you get mud, fire and earth, you get bricks, fire and water, and you get tequila. We also have several modernized versions of what an atom looks like. So Democritus atoms were these small, hard atoms, and then we got a Rutherford atom, and then we got a modern atom, which has all these kind of weird things shooting off of it. So in the 5th century BC, the Greek philosopher Democritus proposed that all matter consists of very small individual particles, which he named atomos, meaning uncuttable or indivisible. A, not, and tomos, meaning to slice. So if you talk about like a computer-aided tomography, CAT scan, that is slicing you up into individual X-ray scans. In the view of Democritus, different properties for what we'd call different elements would relate to the shape of the atom. So something that would be fire would be like a sharp, spiky atom, and something like water would be a round atom. No support was given to this theory by Plato and Aristotle, and just because of how history worked, the Platonic and Aristotelian view came to dominate. Part of that had to do with Aristotle being the mentor for Alexander the Great, who conquered a lot of what was the known world at the time, as well as some of his records being the ones that were preferentially preserved. 1808, you got John Dalton formulating the precise definition of indivisible building blocks of matter that we call atoms. And so Dalton is really the one who we're going to look for as this is the modern view of what an atom is. And so he kind of went back to Democritus and said, hey, this was not a bad idea. And so he's got some rules for this. So in Dalton's view, elements are composed of extremely small particles called atoms. All atoms of a given element are identical, having the same size, mass, and chemical properties. The atoms of one element are different from the atoms of all other elements. Compounds are composed of atoms of more than one element. In any given compound, the same types of atoms are always present in the same relative numbers. 3, a chemical reaction rearranges the atoms in chemical compounds. It does not create or destroy them. So that's that conservation of the law of conservation of mass. So for example, if we take some oxygen, 4 oxygens, 4 O2s, and we combine them with 4 carbon atoms, we're going to end up with 4 carbon dioxide molecules. And so they're always going to be in the same ratio. And anytime you see a CO2 molecule, carbon dioxide molecule, it's always going to have 1 carbon and 2 oxygens. There's the same number of oxygens on over here as there are over here, and there's 4 carbons here, and there's 4 carbons here. Right? We're not creating or destroying matter. Let's say Robert Boyle and some of the other pioneers of chemistry introduced quantitative physics and chemistry. So putting some numbers to things, right? So the idea that we want to make our scientific inquiry numerical was a huge breakthrough, right? Because if you look at something and say, oh, that's green, or oh, that's heavy, well, that's relative to you. Well, I might be seeing that green as a more teal color, and I might think that it's not heavy at all. So if we get away from something that is subjective to more objective, something that's more quantitative rather than qualitative, there's less room for argument or interpretation. 5 grams is 5 grams, whether you measure it or I measure it or a Martian measures it out on the moon Phobos. Okay. Boyle declared that elements cannot be further broken down, and that started to phase out that Greek system describing the elements. All these views are not going to be completely accurate. So metals were not true elements, right? And so there were some refinements that we needed to do. George Stahl suggested the existence of phlogiston. So one of the things that they really did not understand was, or kind of combined, was this idea of phlogiston, which was what we would think of as both oxygen. So when you would take something like a chalk and you would heat it up or something that was an oxidized compound, it would then release oxygen. And then if you were doing combustion, right, you took some wood and you burned it, this phlogiston view would say that, oh, it required some phlogiston in order for it to go. And so we would think of that as being the element oxygen or something like free energy. There were other concepts floating around for really quite a long time, like the ether, so this media through which waves would propagate and sound would propagate and light would move. So, like, what's this wave traveling through? Well, it must be some sort of ether. And we see that today, at least in name, with